Hi, everybody. Thanks for joining us today on the first of 3 sessions today on X-ray binaries at the Chandra Frontiers in Time Domain Science. I'll remind you that our next session is immediately after this one at 10 a.m. starts at 10 a.m. Eastern Time, and the third session is this afternoon, and it starts at 4 p.m. Eastern Time. There's the sessions there on the screen. Our session today is the first X-ray binary session, and our first speaker, if they can begin to share their slides, is Arash Bahramian, coming to us from the International Center for Radio Astronomy Research, Curtin University, and will talk to us about a unique view of variability in exotic X-ray binaries from Chandra. Arash, you're muted.
Yeah, all right, can you hear me?
Yes.
Awesome, thank you very much. All right, I'm going to talk about a bit of about variability in exotic X-ray binaries, especially the ones that Chandra has helped discover and allowed us to study. In the front cover of my talk, you see the globular cluster Terrazon 5 as seen in the optical, and on the other side, you see the X-ray image of this cluster, as I think it's one of the very beautiful examples of cases where Chandra is exclusively the best telescope to study population of X-ray sources in these environments. So given this is the first talk of the X-ray binary sessions, I thought it would be good to just give a quick introduction of the X-ray binaries, which we call binary systems that have enhanced X-ray brightness. And typically they involve a compact object, a black hole, neutron star, or white dwarf, and a companion star. If the companion star is less than a solar mass, roughly, we would call the system low mass X-ray binary. If it's more, it can have other classes and sometimes high mass X-ray binaries. With white dwarfs, they're called cataclysmic variables, and then we have millisecond radio pulsars, which I'll touch on a bit. And then we have chromospherically active binaries, which do not involve a compact object, but they are tidally locked stars that can be bright in X-rays. So there are different classes of X-ray binaries, and there are all around us in the galaxy and other galaxies. However, it's noticed that there is a large density of them in globular clusters, these spherical collections of stars that orbit the galactic center, and they're extremely old and tend to show really high population density of X-ray binaries. For example, this is 47 Tuc, another fantastic globular cluster, and this is how it looks in the X-rays. And the reason for this overpopulation is because while in the galaxy, X-ray binaries are typically formed through binary evolution, that you have two stars that were born together. One of them goes through stages of life faster and becomes a compact object, while the other one is still in earlier stages of life. And if they're close enough, they will form an X-ray binary. In globular clusters, you can do that through encounters, stars running into each other, or binary exchange mechanisms and other things. So that is one of the main reasons that X-ray globular clusters have a higher number of X-ray binaries. So they are an amazing place to go and study different classes of X-ray binaries and their behavior and find them and what is happening to them because of the dynamics. And because of that, there are mainly two groups of systems that I thought to talk a bit about in this talk that Chandra time domain science has helped significantly in studying. One is transitional millisecond pulsars, especially in globular clusters, which I'll touch on a bit, and this is in globular cluster M28. On the other side, black hole low mass X-ray binaries in globular clusters. I will go more on galactic globular clusters. However, this scenario on the other extreme end, when they are very luminous in extragalactic globular clusters, also becomes relevant, because as you see, a common theme in all of these images is that confusion and in being in a crowded place is a problem that Chandra has been able to allow to get over and help us study these systems in these environments. So to start with transitional millisecond pulsars, so neutron star low mass X-ray binaries are thought to be the progenitors of millisecond radio pulsars, and there are many studies. Just to briefly mention some of the points that have been through this studies of these systems. Just a few points. One is that, well, one of the evidences was the first pieces of evidence was detection of X-ray pulsation in low mass X-ray binaries, for example, SAX J1808 by Wynand et al. And that was built. And then in 2009, it was the detection of radio pulsation from a low mass X-ray binary J1023 by Archibald et al. And so this built the connection that there is a missing link between low mass X-ray binaries and pulsars. And it was then in 2013 that detection of actual switching from between the radio pulsation and X-ray pulsation states in an outbursting low mass X-ray binary that made this amazing connection between the two. So this animation you see, it beautifully shows the two states. When you see the green cone that is kind of representative of the pulsar state, and then it swings into the accretion state, a low mass X-ray binary state with X-ray pulsations. So this was observed and discovered in 2013 by Alessandro Papito et al. And it encouraged many studies of these systems. And it's noteworthy that this system, IGR 1824, is actually in a globular cluster. So based on this very brief history, it's important to note that people started going and studying variability in these systems and look at historical data. And I'm going to bring up just a few examples. There have been many studies, and my apologies if I miss any of the important studies. I'm just going to go over a few examples of variability that time domain science that especially Chandra has contributed to. One was after the discovery of the state transition in the outburst of the TMSP in M28, people went back and looked at the archival Chandra data during the time that the source was in quiescence. This was before its outburst, one in 2006 and one in 2013. And they noticed that the source shows this very distinct behavior that during its low mass X-ray binary state, it shows two different modes, as it's now known as, one active mode and one passive mode of luminosities. And the switching between them is actually very quick. This is thought to be connected with propeller regime and still under heavy study. This was, after this, another system that has been a suspect of this class, and state transition confirmed it as a member of the TMSB class, XSS J1227, showed that besides the passive and active mode, these sources can also show flaring and show these massive flares that go up and down. And this is another signature of this class that we haven't seen in other systems that much in this combination. And then long-term studies of these TMSPs showed that, they actually switch between the states on time scale of months, years, and it's actually observable. And then it was a fantastic study that showed a very strong anti-correlation between Chandra and VLA, basically radio and X-ray and radio respectively, when it is switching between these modes. And when it goes into the passive mode, radio gets brighter almost immediately with very little lag. And this was another fantastic signature of these classes. So I bring up these classes as examples because to point out that these particular signatures form various behaviors that are very distinct and allow easy identification of candidates that we can explore further and see if they are actually members of this class. On this plot here, what you see is X-ray luminosity versus X-ray spectral hardness. And this is just to show that these are the three confirmed TMSBs in the active LMXB mode. This is their passive LMXB mode. And this is where they are in a pulsar state, which they are they're members of the redback pulsar family. So they are in this part of the plot. And so these behaviors, these time domain signatures allow very nice, give us very nice clues to search for other candidates. And while the numbers of are still very low, we have 3 confirmed TMSBs, a few other very good candidates. It is good to know that one of them is in a globular cluster. So, and that was in M28, as I showed earlier. And that encouraged us to look at other clusters, and it's been looked. One of them is in Terrazon 5, obviously, because Terrazon 5 has been looked by Chandra for its entire life, for Chandra's entire life, and for this is so it has a very long baseline of observations which allow us to go back and look at variability behavior. So that blue source there, that is Terrazon 5 CX1, and when we looked at its behavior over a long time, so what you see here are all Chandra observations over of Terrazon 5, and we saw that, oh, it popped above 10 to the 33 in this observations and stayed there into the entire Chandra observation. And then again, did it here in 2 observations. These are 2 observations here. But the rest of the observations, it has stayed in this level. So these luminosity levels are kind of resemble state switching. Those red bars at the bottom are times of the radio observations in which the source was detected. And when you look at the observations of when it was in the presumably the bright state, which kind of resembles the low mass X-ray binary state, it shows this variability that mimics flaring. However, you don't see the passive and active mode, the reason being that Terrazon 5 is very far, it's at 6 kiloparsecs compared to the other TMSBs that have been studied in quiescence. And it is very extinguished and hard to study. So its spectral variability and time domain variability, the Terrazon 5 CX1, kind of resembles these TMSBs, and it needs still a lot more studies to be confirmed, but this was an example of how these candidates can be identified using these time domain properties. There's another candidate in 6652b that has been known for a while and has been studied by different groups. And it shows, again, similar behavior regarding flaring and modes. It has been also studied in radio and optical, and in those bands also shows similarities to TMSBs. So one of the aspects that are important for these systems is looking at multi-wavelength behavior of these, and especially radio versus X-ray. And radio typically is representative of compact jet from accreting systems, while X-ray represents accretion. So in this plot, when you look at the top part, it seems that black holes, which are those dark green circles, those are typically at same X-ray luminosity, they have stronger jets, higher radioluminosities. However, this is getting a bit more confusing now that we have seen accreting millisecond X-ray pulsars that are reaching same level. And to show you where transitional millisecond pulsars sit, those are the triangles that are flickering right now in this plot, just to show you. And those are TMSPs. And you see that in the fainter part of the plot, things get very confusing. There are different classes. You have the CVs. These are as flare peaks, so they are not persistently at this level. However, you have some black holes, these are black holes, and you have AMXPs, well, this is an upper limit, and you have TMSPs here. So it gets complex, and it requires a lot more care. I encourage you to listen to the talk by Jennifer, and also there are other talks in these sessions about various aspects of multivalent study of X-ray binaries, not necessarily radio versus X-ray, but other aspects that I encourage you to listen to, see disentangling these behaviors. So zooming in on that faint corner of the plot, which is very difficult to study and now confusing because we have black holes and TMSPs and AMXPs. Black holes, there are a couple of them known and well studied, and then that have been studied well. And then we have the black hole candidates in globular clusters, which are these ones. And these ones all sit there, but we can't really, just by looking at this plot, say that these are necessarily a black hole is the best scenario. And that's where study of time variability becomes important. Now, to give a little bit of, now switching the topic from TMSPs as we go into this confusing part of the plot from TMSPs to the black holes which occupy this part. Why black holes in globular clusters are important is that all bright accreting X-ray binaries so far observed in galactic globular clusters have been known to be neutron star LMXPs. So this is they are either confirmed through X-ray bursts or pulsation. And I encourage you to listen to the talk by Teresa in the neutron star session that she talks about some of these objects. There have been no dynamically confirmed black holes in any globular clusters until recently. Ben Gieser and collaborators found detached black holes from radial velocity studies in the optical, in detached binaries, black holes in detached binaries in 3201. So there's still no confirmed accreting black holes in globular clusters. And so radio X-ray studies is an efficient way to identify these candidates. And because of the high number of sources in these environments, Chandra is an amazing tool to go after these sources. So, and Chandra has studied globular, looked at globular clusters for a long time. So I show in this plot is a subset of globular clusters that Chandra has looked at, not all of them, but the amount of time that it has looked and the level, the luminosity depth that it has reached, we can reach in these clusters. And it has provided us with a fantastic opportunity to study these systems. There have been already multiple black hole accreting black hole LMXP candidates in globular clusters identified through these studies, radio and X-ray and other components. And in M22 by Strader et al., in M62 by Chomiak et al., 47 Tuck X9 by Miller, Jones et al. And later, I also worked on this, and I'll talk about it a bit. And M10, which is another system. And you can see that the companion in each of these systems is different, and they come in various configurations, which is exciting. And there are many other that are under study. As you can see, all these red pentagons are like new candidates. Not necessarily all of them are black holes, but new candidates identified to be studied in globular clusters. Now, I want to finish this talk with a very specific example of time domain science by Chandra that I worked on, and that was on 47 Tuck X9. So as I showed, 47 Tuck has a lot of X-ray sources in it, and 47 Tuck X9 is this pink magenta source that is there, and it's the brightest hard source in the cluster. Basically, if you look at the cluster above 2 or 4 keV, it is the brightest source in the cluster. And even when Einstein looked at it, Einstein telescope looked at it, the coordinates that the high resolution imager has of the source in 47 Tuck is consistent with X9. HSD discovered a blue star as a counterpart for this object, for X9. And then later, significant variability both in UV and X-ray was identified, as you can see. When people looked at the spectrum of it in UV and X-rays, they noticed these very peculiar carbon-4 and oxygen 7 or 8 features that are not very common in X-ray binaries, and they're very rare, besides the fact that the spectrum of the source is very peculiar. There was also hints of a 218-second period, which could have been thought to be spin period of an accreting white dwarf. So it was a candidate cataclysmic variable with a white dwarf accretor and a main sequence donor. However, later studies showed that more observations showed that reduced the significance of the 218-second periodicity. And then later on, Miller-Jones et al. Looked at radio observations of 47 Tuck, and they identified a bright radio counterpart that sits right there. And that's where that is starting to show you the importance of time domain studies. So it sits somewhere that now we know TMSBs are around and black holes are around. So how does it compare to these two classes? And well, 47 Tuck has been observed by Chandra significantly. So we tried to look at it, its X-ray behavior. And here I'm going to summarize briefly the time domain studies of this. So in the 1990s, Rosat had looked at 47 Tuck, and this is that it showed it's variable and it gets bright. So this is X-ray luminosity between 10 to 33 and 10 to 34. So it shows significant variability. And then Chandra ACES observations in 2000 and 2002 also showed significant variability. Then in the end of 2005, 2006, Chandra HRC took an almost 20-day observation with very little interruptions of the cluster. And so it would be very exciting to look and see how this source varies in that, looks in that observation. And this is what we saw. That over 20 days, the source shows this significant modulation with a period of around 7 days. And this period is a bit too large for it to be orbital, based on the companion and other pieces of evidence. This is really unlikely for it to be the orbital period, but it is probably a superorbital period with 7-day periodicity. And it is hard to explain, especially superorbital modulation at this luminosity level. And one possibility is that it could be a warped accretion disk.
3 minutes.
Thanks. But it is very difficult to study further, but it is a very fascinating scenario. Now, this was the superorbital period, but HRC has a rather good time resolution. And if you have 20 days of this data, we can also look for other signatures of variability, maybe orbital period. And we could find it actually. So we looked at the light curve from HRC combined with ACES data from 2002. And when you make a light curve that is joint between the two, the periodogram shows this amazing feature, which is also present in the individual periodograms at 28 minutes. 28 minutes is consistent with for it to be orbital period, and also helps explain the carbon and oxygen features, because that is what you expect from white dwarf. So these time domain features allowed us to identify it as a very different type of X-ray binary, and realize that we are looking at a ultra compact X-ray binary with a white dwarf donor and probably a black hole accretor. And so with that, I just like to wrap up and say that the time domain science that Chandra has enabled us to achieve has been fantastic, especially in these elegant and crowded environments of globular clusters, and from transitional millisecond pulsars to black holes or neutron stars, and also extragalactic ones, ULXs, which Kristen has talked about in the ULX session before. And I hope that I could tell you some of the highlights that I thought to mention about time domain science and X-ray binaries. And with that, I'm going to conclude, and I'm open to questions. Thank you.
Thank you, Arash, for the excellent opening talk to the X-ray binary sessions for today. I think it was very thorough and covered a lot of subject. We have a couple of questions in the Q&A. I'll read those to you. The first is from Tom Macaron, who says, for TER5 and 6652, is the Fermi emission a possible diagnostic of whether these objects are TMSPs? I guess for TER5, maybe the number of normal pulsars provides a large background, but is that the case for 6652?
If I recall correctly, for 6652, Fermi was actually indicative that like it was in support of like presence of a TMSP. So, so if that is my recollection, I hope I'm not confusing it with another cluster. But yes, for Terrazon 5, the background would be too high, I believe, and very difficult to study.
Great. This question is from Tong Bao, who says, thanks for the great talk. For 47 Tuc X9, how to explain the period about 7 hours found in the optical UV band? And could the precession of accretion disk produce the periodic variability with a factor of 10?
So I presume they mean 7-day. That was so this is, I presume they're referring to this. And that's a very good question, if this is what they mean. So this was seen in the X-rays. Please correct me later, and I will continue to engage in this question if I'm wrong. But if they mean this 7-day modulation that is seen in the HRC light curve that I suggest that maybe precessing warp accretion disk might be an answer. I'm not sure, and the problem is that we have tried to study the X-ray spectroscopy, but HRC doesn't provide any good resolution for good spectral resolution. So that's very difficult, and we are going to rely on the ACES data that are over a couple of that don't cover the entire order of magnitude, but do help. So what I said was just a speculation, but I'm not sure if an order of magnitude can be done by that.
Yeah, I think that's the period that Tong is referring to. But Tong, if you want to comment on that in the Q&A, we appreciate that. Okay, we have a question now from Carrie Klojoen, and they ask, if I saw correctly, it seems that globular cluster sources are more radio loud for low X-ray luminosities as compared to galactic X-ray binaries. Any ideas why?
I think that was a very good observation. However, I would say that this is mostly probably a detection bias rather than actually being the case. So globular clusters are typically further away than most of these sources that you see here. So all of these CVs are very close, but the globular clusters are at around between like 2 to 8 kiloparsecs, the ones that we have been studied, most of them. And so it's mostly a matter of the fact that the sensitivity floor is around like 10 to the 27 in many cases. Sometimes if you're lucky and cluster is close and not extinguished, you can get to 10 to the 26. So I think that's more a problem with sensitivity floor rather than actually they behaving differently at this point.
Great. I was gonna comment. I was just appreciating your diagram where you showed the depth that the observations of clusters and the luminosities that you get down to.
This one, yeah.
And I was comparing it to this to see how much of this diagram you can probe, and it looks
so
like in most cases.
So in the x-axis we are fine mostly. It's the y-axis that is the problem. So studying these in radio with ATCO or VLA is very difficult to push the floor down below 10 to the 26 most of the time.
Yeah. Great. We do have a follow-up from Tong, who said, sorry for the confusion, for X9, I remember there is also a period of 7 hours found in the optical band, and he gives a reference here to Niggy.
Oh, yes.
2008.
Yeah, I remember. Yes. Yeah. So, that's why I was not sure if that was referring to that. Yes, I remember that. However, if I recall correctly, we actually looked at that data a little bit. This was done in Tudor et al. A bit more. However, the evidence for it we didn't find much more than was previously noted, and it's not easy to explain either. So all of these variabilities, all of these superorbital variabilities are really difficult to explain.
Okay, and I think we have time for one more question. This is from Solon Ballman, who asks, is the model for TMSPs in the model for TMSPs, is there a disk during the propeller stages in the model or as observed?
So the LMXB state of TMSPs have been actually is still being disputed, and I'd like to point out that there have been speculations that there may be the active mode, it may be actually the enhanced pulsar emission instead of actually being from the accretion disk. There are papers about that. So it is still very, very mysterious and not well established, I would say.
Great. Thanks again for an excellent talk and for an excellent Q&A from all of our attendees. I'd ask our next speaker to start sharing their slides. Our next speaker is Jennifer Rodriguez, coming to us from the Michigan State University, and will talk to us about GS 2000 plus 25, the least luminous black hole X-ray binary.
Hi everyone. As mentioned before, my name is Jennifer Rodriguez. I'm an undergrad at Michigan State University, and I will be talking about GS 2000 plus 25, the least luminous black hole X-ray binary. To start off, an X-ray binary is a binary system composed of either a neutron star or a black hole that is accreting material from a companion star. The accretion disk or the corona will produce X-rays, while the jets will produce radio. And so the radio and X-ray luminosity correlation can be used to study the connection between the accretion disk and the jets, as seen here on the right. As you can see, more high luminosity black holes have been studied and are therefore plotted on the plot on here on the right. But down here, only 3 confirmed low luminosity black holes with simultaneous radio and X-ray observations have been studied. So there are minor constraints here on the lower luminosity relation, and more quiescent black holes need to be studied in order to further understand this lower luminosity trend. That being said, GS 2000 plus 25 is a quiescent black hole with a mass of about 8.4 solar masses, and it is at a distance of about 2 kiloparsecs. It was studied simultaneously in the radio and the X-ray for about 27 kiloseconds. In the radio, there was no detection of GS 2000 plus 25, so we placed an upper limit on the radioluminosity, and then with the X-ray observations from Chandra, we found an X-ray luminosity about 10 to the 30th ergs per second. So therefore, GS 2000 plus 25 is by far the lowest luminosity black hole studied with simultaneous observations in both X-ray and radio wavelengths. On the LRLX plot here on the right, it follows along with the rest of the trend of the low luminosity black holes. But as you will notice, all the low luminosity black holes are slightly below this dotted line, the correlation line. Right now, there's not much that can be said about this correlation, as there is not enough data with the low luminosity black holes, the quiescent black holes. So more studies need to be done of these low luminosity quiescent black holes in order to further understand this correlation and to see if these black holes do in fact fit this correlation. So that's pretty much it. Short, sweet talk.
Thank you. Thank you, Jennifer. That was a lightning talk, by the way, to our attendees who are not aware. That was an excellent lightning talk, quick and to the point. If you have any questions for Jennifer, please feel free to enter them into the Q&A. I have a question. What made you decide to target this particular object? Maybe I missed it.
I don't really know. I just took up the research. It was already like done in a proposal, so I just took it on, and it was very interesting and found some very interesting results.
Excellent. We have a question from Tom Macarone who says, nice result, Jennifer. What is the inclination angle for this binary? Could it be radio faint because of beaming?
I'm not sure of the inclination angle. I would have to further look into that. And as for the second question, the radio beaming, I wouldn't know how to answer that either. I'm sorry about that. It's just really radio faint.
Great. I think that it's very difficult to get simultaneous observations, and this is an excellent target to try to have done that. I think we have 30 seconds left, so I'll ask the question from Akash Garg. Thanks for the talk. Does this black hole source stay always in quiescent state, or has it been seen to evolve?
I believe it was seen going into quiescence. I'm not really sure. It's been quiescent for quite a long time, probably since it was discovered.
Great. Thanks again for excellent lightning talk and for a good Q&A from our attendees and yourself. I had asked our next speaker to start sharing their slides. Our next speaker is Payaswini Saikia from New York University, Abu Dhabi. They will talk to us about Xray binary new early warning system, also called XPNews.
Okay. Hi, everyone. Thanks a lot. It's great to be here with you all today in the Xray binary session. I'm Payaswini Saikia from New York University, Abu Dhabi. And today I will be talking about XPNews, which is a real-time data analysis pipeline to monitor both neutron star and black hole Xray binaries in the optical wavelength and alert the community of new outbursts and other peculiar activities. Sorry. Just a second. Perfect. Okay. So after Arash's talk, we now have a proper introduction to Xray binaries. So just very briefly, Xray binaries are binary star systems that consist of a star in orbit with a compact object like a black hole or a neutron star. These Xray binaries are really hard to find unless they go into an outburst. The transient Xray binaries, they can spend like years to decades in a state of quiescence, being faint and feeding at a very low accretion rate and making it extremely difficult to get detected. So these sources, they are almost always first detected by some X-ray all-sky monitoring satellites like MAXI, Integral, or SWIFT. But because of the sensitivity limit, these telescopes only detect sources which are typically above like 10 raised to 36 ergs per second or more. So for example, here I'm showing you MAXI 1659, which was discovered during an outburst in 2010, when it was almost 6 orders of magnitude above the quiescent flux level. So we don't know what happened before that. We don't know what triggered the outburst, how the system changed, or how it came out of quiescence, etc. The problem is that due to the sporadic nature of their start times and lack of regular monitoring, currently we do not have proper ways to predict exactly when these outbursts will happen. And hence it is notoriously difficult to monitor these sources in a way that we can study this initial rising stages of the outburst. So hundreds of Xray binary outbursts have been observed over 50 years, yet how these outbursts themselves start is very poorly understood. So currently, the most widely accepted explanation for outbursts in transient Xray binaries is the disk instability model, which predicts that these outbursts are initiated by a thermal or viscous instability in the accretion disk. So in quiescence, the cold disk fills up with matter until at some radius, its temperature reaches a critical value, which is needed to ionize hydrogen, and then it triggers an outburst. So these heating fronts propagate through the disk, bringing it to a hot, bright state, and the X-ray emission comes, or the X-ray rises when it reaches like the innermost regions. This instability model, although it is very well established for dwarf nova outbursts, that means accreting white dwarfs, but for X-ray binaries, to date, no observations have constrained this triggering location and conditions in the disk due to the lack of data during this initial rise stages. Okay. So currently, the only way regular monitoring can be used to detect the start of new outbursts is with optical telescopes. So we are monitoring around 40 to 50 X-ray binaries, both black hole and neutron star X-ray binaries, for almost 10 years now with the LCO observatory, which is the largest global network of robotic telescopes ever constructed. So we have sites here in Texas, in Chile, Tenerife, Tibet, Israel, South Africa, Australia, and there are almost 40 to 50 X-ray binaries that are being regularly detected, even in quiescence with these optical telescopes. We are using different filters, mainly the V, R, and IP bands. And the cadence is about once a week, unless when the source is of particular interest, like it's like going to be in an outburst or in some flaring stages. And the data we get with this kind of observations is really promising. In 2019, for example, we detected initial optical rise for this neutron star X-ray binary SEX 1808. We alerted the community with ATELs, and almost 12 days later, it was detected in the X-rays, and the source went into an outburst. So by giving this kind of very timely update, we hope to be able to look at this kind of, for example, the radio X-ray correlation that we saw in Arash's talk, in the rise phase and then in the decay phase, if there are differences, because these things can tell us a lot about the physics that is going on. So our data set shows this initial onset of several outbursts days before it is detected in the X-rays. So this is just a simple table of our first optical detection and the first X-ray detection of few of these sources. And we see that in optical, we have detected it before the X-rays, but in the previous years, we have often noticed these onsets too late due to the lack of an automated pipeline that analyzes the data in real time. Like we had to do this analysis ourselves, so it was taking much more time. But now we have developed and implemented a real-time pipeline for our X-ray binary monitoring project. This is called X-ray binary new early warning system, or XPNews, which interrogates the LCO data several times per day, flux calibrates the data, checks for flat reduction errors, produces real-time light curves, and automatically alerts us when it thinks that there is something interesting. For example, outburst is beginning, some flaring is happening, or the source is going to reach quiescence or something like that. So with XPNews, the moment we confirm the outburst, we alert the larger community. And with our collaborators at different institutions, we quickly go for rapid multi-wavelength follow-up by using observations with X-rays like AstroSat, NICER, radio telescopes like EMI, MeerKAT, VLA, etc., and also millimeter range telescopes like ALMA. And we are very happy that now we also have Chandra approved time, which, because of its high sensitivity, would be very useful to detect this initial rise of the sources, just going out of quiescence. So the idea that we have is that as soon as we detect an optical flux rise with XPNews, we immediately trigger both SWIFT and the second LCO optical observation. Now, if SWIFT yields a non-detection because of its sensitivity limit, but the second optical observation, on the other hand, confirms a new outburst, then we immediately trigger the Chandra TOO to have a look at the source with Chandra. Till now, we have been able to detect faintest changes in optical amplitude as the source comes out of quiescence and alert the community about many new outbursts happening in both neutron star and black hole X-ray binaries, like we did, for example, the latest 2020 Equil X1 outburst. We have also been able to obtain rich multi-wavelength data sets of different X-ray binaries that are of particular interest to us due to their signs. For example, just an example here is GRO 1719 light curve in optical X-ray and ultraviolet wavelengths, which are very useful in studying things like the variability of the source, the fractional RMS, like multi-wavelength time-varying spectral energy distributions, color magnitude diagrams, fast timing studies, correlations between different multi-wavelength observations, and dive deeper into the physics of the source. And we are now trying to, this is the most interesting, that we are trying to constrain the disk instability model, which answers how these outbursts occur by looking at the long-term behavior of these sources. For example, the disk instability model predicts that outbursts are initiated by a thermal or viscous instability in the disk, And hence, it says that we should be able to see a slow optical rise in between these different outbursts that we see in a source. And we actually do detect it in few of the sources, like GS1354 that I'm showing here. So here is the 2015 outburst of the source. And you can see the the slow optical rise in all the three filters, V, R, and I, till it entered the outburst phase.
3 minutes.
So, yeah. So same with the source, 1357, which is being studied by one of the students of NYUAD. Between the 2011 and 2017 outburst, we detect this rise of the optical emission as expected by the disk instability model. But it's very interesting that the most recent outburst of this source, which happened in 2019, shows that the trend is very different. We see a slow delay in the, not the rise of this optical emission during quiescence, and it's exactly opposite of what was predicted by the model. So this kind of monitoring is helpful in observationally constraining the models and in understanding how these outbursts are triggered and what is happening in these X-ray binaries during the outbursts and during quiescence. So finally, to say that XPNews is a real-time data analysis pipeline that we have to look at the optical light curves of these many of the X-ray binaries. We have more than 10 years of optical monitoring of 40 to 50 low mass X-ray binaries. And by triggering the X-ray early on, the idea that we have is that we want to test predictions from these disk instability models about how outbursts are triggered. We want to study the early rise phase at different wavelengths, detect state changes, and predict when new outbursts might occur. So we have a lot of data, and if you have any particular object that is interesting for you, you can just write to us and we will be happy to collaborate. There are lots of interesting sources that we have in our collection now. Thank you.
Thank you, Payaswini. That was a really interesting talk. So I was going to ask a question about the data, and it sounds like it's not publicly distributed, but it is available upon request.
Yes, so it is actually we are putting the light curves as public data already. But to get the complete data set, if you want to have a look for different bands, for example, then it would be better to write to us. But yeah, finally, the idea is that once we have the pipeline and the website completely ready, then at least the light curves, the real-time light curves will be updated in the website.
Great. We have a couple of questions. This is from Tom Macaron. Is the issue that the X-rays are fundamentally rising later, or that optical telescopes are more sensitive than the X-ray all-sky monitors?
Yeah, that's a very nice question. At least in Chandra, at least the Chandra sensitivity is good enough to have a look at when the outburst is happening, that we have seen in few of the sources. But even from the disk instability model, if we believe in the disk instability model, then we would expect that the optical, because it is coming from the disk, will rise before the X-ray, which is coming from the innermost part of the inner part of the disk. So that is kind of expected. But even in Chandra, where we can see some sources in quiescence, we see that from quiescence to go into outburst, it takes a bit of time, more time than what we see in optical.
Great. These two talks are a little bit similar, so I'm going to ask both of them simultaneous at the same, or one after the other. This is from Yash Bhargava, who says, nice talk. Where can we access the list of sources which are being monitored? And Victoria Grinberg asks a similar question. Thank you for the great talk. This is a super exciting, important work. You mentioned that you monitor 40 to 50 transients. How do you decide which transients are getting monitored? So where's the list and how do you decide?
That's a good idea, a good question, especially the one that asks how we have decided. So we are, for black hole X-ray binaries, we are observing most of the black hole X-ray binaries, unless there is issue with things like absorption and the problems due to which we can't get proper detection. For neutron star right now, because our group was more more interested in black hole X-ray binaries. So the neutron star, we do not have a lot of neutron star in our list yet. But yeah, we are continuously monitoring few of them. And whenever we find something interesting, we put them to the list. We have a lot of regular targets and non-regular targets. And it is up on the website called XPNews at NYUAD. I'll write it down in the chat box. Sorry.
Great. And we have 18 seconds, so I don't think we're going to get to Tom's last questions, but you can see it in the Q&A. If you could put a response to it, a response to Tom, that would be great. And I'll ask the next speaker to start sharing their slides.
Okay, thanks a lot.
Mm-hmm. Thank you again for an excellent talk. Our next speaker is Andreas Zezas from the University of Crete and CFA. And will be speaking to us about extragalactic X-ray binary populations. Andreas, can you try to share your slides?
Yes, I'm trying to do this right now. Okay,
Perfect. Yep, great.
Okay, perfect. Thank you very much for the invitation. So I'll try to give you a summary of the recent work that has been done on the population of X-ray binaries in nearby galaxies. And although I'll try to give a literature review, I'd like to acknowledge the contribution of my collaborators, and particularly graduate students that have been working with me in the past few years, underlined here. So I'll start with a customary slide about why bother about X-ray binaries. And the first obvious answer is that they're perfect probes of compact objects. Is the most efficient way of identifying compact objects, particularly in other galaxies. Also, because X-ray binaries is a phase in binary evolution, are a very efficient tool for understanding binary evolution and their different complex phases that we'll see in a second. And of course, they are often intermediate state in the formation of gravitational wave sources or short GRBs. So it's a very important tool for understanding the pathways that create those very energetic events. And finally, X-ray binaries is the main source of X-ray emission in galaxies, particularly in the hard X-rays above 2 keV. And especially over the past almost 10 years, there has been quite a bit of work on the importance of the X-ray emission from galaxies and binaries in the very early universe, particularly in the era of reionization, where they may play an important role in heating the intergalactic medium. And this has major implications for formation of galaxies during the evolution of the universe. So for all these reasons, X-ray binaries are really an important tool. It's a very important, I think, to study and understand their formation and evolution. So although we have known X-ray binaries since the beginning of X-ray astronomy, there are still a lot of things that we don't really know and we don't understand about their evolution. These things include, for example, what happens during the supernova explosion, like when the primary star becomes supernova, they often receive a kick. So a major question is how strong are these kicks and how they affect the evolution of the binary system. Another question is what happens after the supernova? What is the mass spectrum of the formed objects? How massive black holes can we form? What is the fraction between black holes and neutron stars, which has important implications for the binary population that we observe, and of course for gravitational wave sources or short GRBs that are going to be observed later. And or another phase that is very important is the common envelope phase, where the two components of the binary may spiral within their common atmosphere. And this is a very, very strong filter in the evolution of the binary, and it tends to destroy a very large fraction of the binaries. Eventually, they will merge, and in the end, we will not have a binary anymore. So this is a very important phase that determines the fate and future evolution of a binary system. And again, we know very, very little about how this phase behaves. So So all these factors, though, do affect the populations of X-ray binaries. They do affect the numbers of X-ray binaries we observe. They do affect their properties, like X-ray luminosities, their orbital periods. So by studying the X-ray binaries, we can actually infer quite a bit of information about the complex phases that they go through during their evolution. Now, one could say, why not do this in the Milky Way? So the Milky Way is great. We learn a lot of deal about details of the binary systems, in particular about accretion physics. However, Milky Way has a few, Milky Way or nearby galaxies have a few issues. The main issue is distance determinations. There is a significant fraction of the binaries in the Milky Way for which we don't know their distances. However, if we have binaries in another galaxy further away, we do know the distance of the galaxy, so we do know the distance of the binaries from us. So it's very easy to calculate their luminosity. It's very easy to calculate, to study their the luminosity of the donor stars, for example, or the accretion luminosity. Another important reason is that in the Milky Way, effectively, you can observe only a fraction of the galaxy, exactly because we are sitting inside the galaxy. Whereas in other galaxies, we can study, especially if they're face on, we can study a large fraction of the population, and most importantly, study their connection with the local star-forming regions. And the last reason, which is very important, is that the Milky Way is only one galaxy. It has stellar populations that cover a rather narrow range of metallicities. And again, they do cover a wide range of ages, but we have only a few stars at a given age range. So by extending our studies in other galaxies, we can cover a very wide range of environments. So for example, here in this plot, we do see a plot of the star formation rate against the stellar mass of all known galaxies within a volume of 200 megaparsecs. So this is from a sample of galaxies that we compiled recently for a ULX study called Hecate. And so we have detailed information on star formation rates and stellar masses, sizes, and so on for the galaxies. Now, the Milky Way or the local group galaxies would be only a few dots within this 5 order of magnitude space in stellar mass and star formation rate. Instead, the hatched areas here indicate the regions, the regions of this parameter space that have been covered by Chandra and for which available data exists in the Chandra source catalog too. So this gives us an idea of the very broad parameter space in stellar populations that we can study by extending our studies of X-ray binaries to other galaxies. So by studying other galaxies, we can investigate compact object populations in a wide variety of galactic environments. And this is particularly important because this way we can study the formation and evolution channels of different types of accreting binaries that might not be present in our galaxy or even the local group. So to give you an example, these are a few examples of observations with Chandra of nearby galaxies. So up here we have an early type and a late type spiral galaxy. So here we have irregular galaxies. Here we have an elliptical galaxy. So we do have a very wide variety of environments that can give us information about different types of X-ray binaries. So how do we go about X-ray binary population studies? There are two main tools that we're using. The first is to study the X-ray binary formation rate, which is done by means of scaling relations that I will discuss in a bit. And the second is by studying the X-ray luminosity distributions of X-ray binaries, the so-called X-ray luminosity function. Now, both generally require the synergy of X-ray and optical infrared observations. The need for the X-ray observations is obvious. I mean, we have to detect the X-ray binaries. The optical and infrared observations are used either to characterize the X-ray binaries or to measure the properties of their host galaxy. That is star formation rate, stellar mass, metallicity, age of stellar populations, and so on. So I will start by discussing the X-ray binary formation rate. So even since the early Einstein days, scaling relations between X-ray luminosity and luminosity in other bands like optical or infrared luminosity has been used in order to understand the origin of the X-ray emission from galaxies. Now with Chandra, and to some extent with XMM, we can perform detailed studies of nearby galaxies, not only study their integrated emission, but also study the populations of individual binaries. But also now we can perform those studies in cosmological distances, where we can observe more extreme objects and extend our census of star formation rates over several orders of magnitude. Like, for example, this is one of the first plots were done in this context. We do cover almost 4 orders of magnitude in star formation rate from rather weakly star-forming galaxies to extreme star-forming galaxies that we see in high redshifts. Similar studies are being done in early type galaxies where we're dominated by the so-called low mass X-ray binaries, binary systems that have a low mass donor star with mass smaller than a solar mass. And again, here we care about the X-ray output as a function of the stellar mass, or equivalently the near-infrared luminosity of the galaxy. However, it has become clear that in spiral galaxies, in typical spiral galaxies, things are a bit more complicated because they are not dominated neither by high mass binaries solely, nor by low mass binaries exclusively. They have a mix of both populations. So the scaling relations that have been developed for these systems include contribution from star formation rate, which is proportional to the young X-ray binary systems. These are the high mass binaries, and the contribution of the stellar mass, which is proportional to the low mass binaries, the older stellar systems. And those scaling relations are usually plotted in terms of the X-ray luminosity per unit star formation rate of the galaxy as function of the specific star formation rate of the galaxy, that is, star formation rate per unit stellar mass. So in the high specific star formation rate part of the diagram, where we have actively star-forming galaxies, we are dominated by high mass X-ray binaries, and we have a constant Lx per star formation rate ratio, which is the same effectively as the ratio we saw here, the slope of this relation. Whereas in very low specific star formation galaxies, which are dominated effectively by the older stellar populations, the X-ray luminosity is proportional to the stellar mass. In intermediate regions, around specific star formation rates of 10 to the minus 10, is where we have a mix of high mass and low mass binaries, and we have to worry about the contribution of both components. So those studies, however, have been based on integrated properties of the galaxy. So what happens when we look in subgalactic scales, in smaller scales, if we try to dissect the galaxy in smaller pieces, and we measure the X-ray output for smaller regions of galaxies. And this is a study that was done by Kostas Kourbadzakis, a grad student of mine, where we see the X-ray luminosity as a function of star formation rate in 4 kiloparsec scales of a few nearby galaxies. And what we see is that the scaling relation characterizing in, the entire galaxies continues all the way down to very low star formation rates. But in extremely low star formation rates, the relation tends to level off. And this is the result of the contribution from the low mass X-ray binaries, because we have extremely low star formation rate, and really the X-ray emission is dominated by the underlying low mass binary population. Now, however, this is important because it shows that even in extremely low activity galaxies, we would expect this scaling relation to hold to very low star formation rates. Now, in terms of luminosity functions, what we see here is the latest and most complete study of X-ray luminosity functions in nearby galaxies. This is a sample of about 40 galaxies studied by Brett Limmer, and they cover a wide range of specific star formation rates, a wide range of star formation rates, stellar masses in nearby galaxies. And so those luminosity functions were parameterized by a broken power law. So these are the two slopes of the power law. And we see that there is quite a bit of variation. And this variation, based on what we have seen, is the result of the different populations of X-ray binaries. This is the result of the population of high mass and low mass binaries. So when we go and calculate the X-ray luminosity function by taking into account the star formation, the specific star formation rate in the regions where the binary is. So we dissect the galaxy and we calculate the combined luminosity function for regions that have high specific star formation rate and regions that have low specific star formation rate. We get these results. So in the left, we have the X-ray luminosity function for regions that are dominated by high mass X-ray binaries, regions that have high specific star formation rates, and we see that they follow a very nice straight power law with a differential index of 1.66, and which is very consistent with what we have been observing for in other studies of integrated of individual galaxies. And in the right hand, what we see is again the differential luminosity function of the binaries associated with regions that have low specific star formation rate. So these are dominated by the low mass X-ray binary populations. And we see the typical broken power law luminosity function that has been observed in L-type galaxies, for example. And the break is at a luminosity of about 2 times 10 to the 38. And the slopes are similar to the slopes that we see in elliptical galaxies. So now we start having a more comprehensive picture of the high mass and low mass binary populations in a sample of nearby spiral galaxies. Now, however, we can go one step further, and what we can do is for our nearest galaxies, we can actually go and identify the optical counterparts of the X-ray binaries and place them on a color magnitude diagram that we see here on the left. So this is a color magnitude diagram of all the stars in a region of the M81 galaxy. The red stars here indicate the location of the optical counterparts of these of the X-ray binaries in these regions, and for example, we can isolate the ones that are associated with early type stars here on the main sequence, and we can calculate the luminosity functions of the high mass X-ray binaries, the luminosity functions of the low mass binaries, but even we can go one step further. We can calculate the luminosity function, the X-ray luminosity function of supergiants, of OB main sequence stars shown here in blue, and so on. So, so now we can go and start studying the X-ray luminosity function of different subtypes of X-ray binaries depending on their donor stars. And this is pretty much work in progress, but it's a very, very strong tool for comparing with theoretical models for X-ray binary populations, because now we can really probe the physics of the formation and evolution of different types of X-ray binaries, rather than lapping together all X-ray binaries observed in a galaxy. However, even from the first theoretical studies, it has been recognized that there is significant evolution of the X-ray output of a stellar population as a function of age. So here, for example, we see the X-ray luminosity that is produced by a stellar population of 10 to the 10 solar masses form at time 0. And what we see here is how the X-ray luminosity evolves as a function of time. And we see that quickly declines. Then there is a bump around 50 megayears. Remember this number in a bit. And then it starts declining around 1 gigayear. So this is this is what we would expect from theoretical models. In the left now, what we see, in the right here, we see how the luminosity function would change for different metallicities. And what we see is that higher metallicities tend to produce higher metallicity systems. This is something that was suspected even from like 20 years ago, but now there is theoretical proof. And as we will see in a second, there is observational proof as well. So what is the observational evidence for age dependence? There are some systems which we have looked at, and they show indications for variations of the luminosity of the X-ray binaries in different regions. One such system is NGC 2276. This is a spiral galaxy that is falling in a group of galaxies. And the intergalactic medium from the group is compressing this side of the galaxy. So this galaxy is harassed by the intergalactic medium, and the compression front creates intense star formation in the side that is falling towards the group. So, and this is seen here by this beautiful HST image of the galaxy that we obtained about almost a year ago. And so what we see is that the side that is falling towards the group is lit up by young recent star-forming galaxies. If we look in Chandra, we see that this side has more luminous X-ray binaries. It doesn't have necessarily more binaries, but has more luminous. And this is shown here in the histogram of the luminosities, where the green histogram is the side, is the compressed side. The red histogram is the other side of the galaxy, and we see that the binaries residing in this side of the galaxy tend to have systematically higher luminosity. Now, this effect has also been seen in when we try to dissect other galaxies like M81. This is work done by Brett Limmer a few years ago, and what they did is they calculated the age of the stellar populations in different regions of the galaxy, and they compared the X-ray luminosity per unit stellar mass as a function of the age. And this is shown here by the black points, where we see that is systematically decreasing the X-ray output per unit stellar mass, systematically decreasing as a function of age. And this agrees very well with the theoretical models that we saw early on in a few slides ago. We can do the same thing in a lot more detail in a local group, where we can really measure with exquisite detail the star formation history in different regions of the galaxy. And we did this in the Small Magellanic Cloud, where we observed with Chandra regions that probe different stellar populations with ages ranging from 10 up to about 100 megayears. So by looking at the column-magnitude diagram and the location of the X-ray binaries on of the optical counterparts of the X-ray binaries in the column-magnitude diagram, we can associate them with individual bursts of star formation, and then we can go and calculate the number of X-ray binaries per unit star formation rate or per unit stellar mass formed at the particular star formation event, or per number of OB stars that we see right now as a function of the age of the stellar populations. And all these three metrics of the high mass X-ray binary formation efficiency agree to the fact that at ages between about 20 and 50 megayears, there is an enhancement in the production rate of X-ray binaries, and then it declines quickly at higher ages. And this is actually agrees fairly well with the presence of a bump at those ages in the expectations from the theoretical models. However, one note of caveat, and this is from the work of Kostas Kourbadzakis that was published recently, is that when we compare with different star formation indicators, we need to take into account the sensitivity of different star formation rate indicators on the age of the stellar populations. Like, for example, even UV, which we consider as a good indicator of young star formation, young stellar populations, UV is actually sensitive to stellar populations of ages up to 100 or even 200 megayears. So if we wish to study the parent populations of high mass binaries, we really should use H alpha. So in this plot here, we see with this line, the gray dashed line, and the black dashed dot line, the sensitivity of H alpha or 8 micron luminosity on stellar populations of different ages. So if we really want to study the formation rate of high mass X-ray binaries, we should really compare with an indicator that is sensitive to timescales that are relevant to the formation of high mass binaries. This is timescales of about 10, 20 megayears, and H alpha is really the perfect indicator for that.
3 minutes.
Okay. So the last, so another thing is the metallicity dependence that I mentioned earlier, and there is now a growing body of evidence that as we go to higher metallicities, the either the X-ray luminosity per unit star formation rate or the number of luminous sources is decreasing. Or in other words, lower metallicity systems tend to have higher luminosity sources and overall larger luminosities. And this is a result that is really hot off the press. This is a paper that was accepted a couple of days ago. So this is a study of a ring galaxy where we measure the metallicity in different regions. And when we go and plot the X-ray luminosity per unit star formation rate as a function of metallicity, these are the color points here. We do see that lower metallicities do have higher X-ray output per unit star formation. One thing here that is very important is that those regions share stellar populations of the same age. So we do control for the age of the stellar populations, and what we see here is clearly a metallicity effect. But this is a session about X-ray timing, so I should say a few things about X-ray binary evolution, X-ray binary variability. So we do know that X-ray binaries are variable, and they do undergo outbursts. So this is a typical outburst for a black hole X-ray binary in our galaxy that starts from a low luminosity and then has an outburst and then it returns back to a low luminosity. However, when we study other galaxies, there is one problem. Our typical sensitivity is up there or at best down here. So we don't really have the sensitivity to study really the quiescent population. This can only be done in local group galaxies. So all the variability we are talking about is variability at really within the evolution of an outburst. Unless we're talking about transient sources, which come and go. And again, there is an issue that we don't really know if a transient source really has disappeared or has just fallen below our selection, our sensitivity. So, so for this reason, most variability studies are focused on ULXs, where we study the spectral variability, and only few sources have been studied. Only few studies have looked at lower luminosity sources, and those mostly in local group. And a limitation of this is because in order to study other galaxies, we need systematic monitoring, and only a few galaxies have been studied systematically. And one of the first results that became clear from these studies is that thankfully the X-ray luminosity function of binaries does not depend on the variability of the X-ray binaries. So an individual snapshot of a galaxy can give us a good representation of the binary populations. Yes. However, it looks like the variable sources are really dominating the faint luminosity end of the binary of the luminosity function, and the high luminosity end is really dominated by persistent sources. So looking to the future, really a way to study in more detail the binary populations and their variability is to have a more sensitive telescope that in shorter observations can observe more galaxies and can perform repeat observations of those galaxies in time scales of a few weeks or even a few months in order to study the variability of the binary populations. So to summarize, I think I hope I convinced you that so far we have a good understanding of the average demographic of X-ray binaries in other galaxies, and we're starting to understand now the systematics of these demographics, like their dependence on star formation rate, metallicity, on star formation rate, age, and metallicity. And this in turn is going to be a key factor for understanding X-ray binary evolution by comparison, through comparisons with X-ray binary formation evolution models. And looking to the future, what we would need right now from Chandra is to perform more long-term monitoring campaigns of nearby galaxies in order to have more systems, more types of galaxies for which we have variability information. And from future observatories, we would like to have the spatial resolution of Chandra and high sensitivity in order to continue this, this great work. Thank you.
Thank you, Andreas, for excellent talk. I was thinking about the timing of your talk, and I think giga-year timescales is a good is a good time domain subject. I don't know if we'll have a giga-year of Chandra monitoring though, but that's a joke. So we have a question from Tom Macaron who asks, what cadences would be important for monitoring?
That's an excellent question. Given that the typical outburst timescales for galactic binaries is of the order of several weeks or months, I would suspect that monthly monitoring would be ideal, but monthly monitoring going over timescales of 1 or 2 years. And this has the added benefit that it gives us a more complete picture of the populations, because now we can estimate what is the emerging population that we haven't seen in individual observations, but also it gives us a picture of the duty cycle, how much time a binary that we observe spends on a non-state or an off-state. Of course, we have no hope of detecting variability of binaries like GRS 9015 that has an outburst lasting more than a decade. But for the typical outburst timescales, monthly monitoring over several years, over a few years, would be ideal.
And Tom asks a follow-up question. Given the thermal constraints on Chandra, are there interesting galaxies where we can do monthly monitoring over a whole year? Say some that might be in cold pitches or...
Yeah, that's a very good question. This is something that we should look into. From our experience over the past Chandra cycles, it has been very hard to find good targets that are in cool pitch angles.
Right. Any additional questions? And I'd like to offer the panelists, you cannot use the Q&A feature, but if you have a question for Andreas, you can raise your hand and you can ask it. One thing that came up in another session was this Chandra cooling targets program that we had, the special call, but it did not allow multiple observations of the same object. But I could imagine there could be a case made where such a monitoring program like this, if it was in a cool pitch, would be ideal.
Exactly. And the good point about this type of monitoring is that it's not strict at all. I mean, it doesn't matter if it slips by a week or so. That should be fine.
Okay, if we have no further questions for Andreas, if we have any questions for any of the speakers, feel free to enter them into the Q&A. I'll give that a minute before wrapping up the session. Great. Okay, thanks everybody. I'd like to thank all of our speakers again for an excellent kickoff to this day of X-ray binaries. Sorry for the feedback. I'd like to remind you that our next session, oops, sorry, is that better? Yes. Starts in about 30 minutes, and it's on X-ray binaries as well, and it'll start with Joy Nielsen. Remember, that's going to be in a separate link, not the same session that you're in now. So please enjoy your 30-minute break, and I'll see you again, hopefully in 30 minutes. Thank you, everybody.